Hey everyone, today we're going to be talking about the heterocyclic amines. So these react very similar to benzene rings or aromatic rings in general. This is because of the pi electrons in the sp and unhybridized lone pair, or sorry, unhybridized p orbitals, the lone pair pi electrons that are in these orbitals. And so if we were to look at something like pyrrole, which will be one of the compounds we look at first, this compound is aromatic, which is why it reacts similar. It's actually a little bit more reactive. So it's more reactive than benzene to electrophilic aromatic substitution. And if we were to look at the orbital structure of what pyrrole looks like, even though we see that it has no double bonds to the nitrogen, we actually have an sp2 hybridized nitrogen here. And in each of the pi electrons over the carbon, we have um, unhybridized p orbitals that exist in there, and then the lone pair in the nitrogen also participates in resonance. So these are parallel to these other p orbitals. So these are the unhybridized p orbitals, and these allow for aromaticity. And so because these allow for aromaticity, it means that this proton right here, or this nitrogen, is not as basic as a typical amine slash arylamine, because protonation will remove aromaticity, right? And aromaticity is a special form of stability. And so since it's extra stable, it doesn't want to remove that proton to remove this aromaticity. And so we can synthesize pyrrole, so we'll talk about pyrrole and imidazole, from furan, which is exactly the same as pyrrole, except it has an oxygen in the place of nitrogen. And if we did this in the presence of aluminum oxide, ammonia, and water and heat it up, we can then synthesize our pyrrole ring. And with the pyrrole, we can then undergo electrophilic aromatic substitution, and it's more reactive than benzene. Remember I said that, more reactive than benzene. And usually this is going to happen on the C2 carbon instead of the C3 or C4 carbons because of resonance. So because of resonance, typical electrophilic aromatic substitution reactions, like ones we have talked about, for example, are alkylation with Friedel Crafts. These types of reactions will still happen. They'll just happen on C2 because if we look at the uh, sigma complex that we form with imidazole, so if we start here, sorry, not imidazole, pyrrole. Imidazole will be similar though. If we were to look at substitution at the C2 position, that means that we eliminate this pi bond here. And let's see, we can use nitration as an example. So if we do this at the C2 position, we can have a positive charge on the nitrogen, NO2. Like I said, this is going to be nitration here. And this can undergo 3 different resonance structures. NO2 plus H. This can then move there. Now we have the lone pair there, so it's not negatively positively charged anymore. Double bond here, NO2 and H, and then abstraction of the hydrogen, moving the electrons back into the pi system will get us our final product. Whereas if we were to do this on the C3 position, NO2 and the positive charge here with the hydrogen, this would only undergo 1 extra step in resonance here. Let me draw this a little neater. Where we get the lone pair moving there and the positive charge moving onto the nitrogen, which would then go to our uh, our final product there, which would just be re-aromatization, and the double bonds go back to where they are. So this, because this has 3 resonance structures and this only has 2 resonance structures, C2 is favored over C3 electrophilic aromatic substitution, which is going to look similar. Looks like this. Reacts the same because the pi system for imidazole nitrogen there, lone pair. The other lone pair is not parallel to the lone pairs here. And so that's why we still have the aromaticity. That lone pair on the second hydrogen doesn't participate. This also makes this a slightly basic amine here, because, or even a slightly acidic if it gets protonated. But we can actually protonate this to then create a positively charged amine here, because that does not destroy aromaticity, right? So for imidazole, this doesn't destroy aromaticity, which is important because then this nitrogen doesn't affect the reactions in any other way, except that the position is still preferred to react on the C2 carbon, right? So this extra nitrogen here doesn't affect the aromaticity at all. So pyrrole and imidazole have very similar reaction schemes. The next, and these are important rings because these usually form ring structures for important vitamins, or the imidazole is important because it forms the R group for a histidine in amino acids and proteins. And so the next ring structures that we're going to talk about are pyridine and pyrimidine, be the benzene analog with the nitrogen. So something like this. We have a lone pair on this nitrogen. This has a pKa that's roughly around about 5.6, sorry, 5.25. So it's more basic than pyrrole, but still less basic than an alkylamine. And if we were to look at the orbital structure of pyridine, it would look something like this. we have our p orbitals, and each one has a single pi electron in it that then participates in resonance. And the lone pair on the nitrogen is not in a unhybridized p orbital, but is an sp2 orbital. And so this is still less basic than a alkylamine because alkylamines have sp3 orbitals. And so this is going to have less s character than an sp2 orbital, right? So we have one unhybridized p orbital, so it's not as p in character. And sp2 electrons are closer to the nucleus. And that means that they're going to be less available for bonding, which means that it's going to be a less basic. It's not going to abstract hydrogen as easy. It's going to be a less basic amine. So that's why this is still, it's more basic than pyrrole, but it's going to be less basic than an alkyl amine. And so pyridine and pyrimidine are both similar. In this way, pyrimidine is just the sixth member ring that has two nitrogens as well. And so these also can react similarly to the other heterocycles that we talked, imidazole and pyrrole. These reactions are a lot harder than with pyrrole or benzene. Right, so this is the low reactivity of pyrimidine towards electrophilic aromatic substitution, right? And so we can brominate pyrimidine. However, it usually requires high temperatures and then occurs in the 3 brominated product, right? So we only get about 30% of this, right? So it's not very effective. And so this is caused by a combination of factors. Because this has a pKa around 5.25, that means that we can form acid-base complexes similar to what we saw for our other amines, right? So if we had a um, Lewis acid or a base, say H2SO4, and our pyrimidine, then we can have our acid-base complex, which would be the protonated pyrimidine. And as soon as we add this positive charge to the ring, now this becomes deactivated. And when it becomes deactivated, it'll cease reacting anymore. For the low reactivity is that pyridine has a dipole moment that points towards the electronegative nitrogen here, which means that these carbon atoms are more positive in character, which makes it harder to undergo electrophilic aromatic substitution because they can't stabilize that positive charge, right? So it's the same reason that when we have electron donating groups on the aromatic ring, it stabilizes and activates the ring. If we have electron withdrawing groups, it does the opposite. The fact that we have a nitrogen here does the exact same for this ring, right? So we have electron withdrawing groups and makes it harder to substitute on these more positive carbon atoms on the ring. We have polycyclic heterocycles. And so these occur in nature a lot. The purine, the pyrimidine that we talked about last time, pyrimidine, which was something that looked like this. This forms the bases for 3 out of the um, 5 bases that we have for DNA and RNA. These are for bases for DNA slash RNA. And then we have some polycyclic heterocycles, and we can have purine rings, which form the other 2 bases, adenosine and guanine. And so purine rings are going to look like this, where we have a pyral looking ring structure attached to a pyrimidine looking one. And so these form the bases for both DNA and RNA, G and A, and these ones form the bases for DNA or RNA, which would be A, C, not A, U, C, and T. And so these can undergo electrophilic aromatic substitution, but similar to pyridine and pyrimidine, this is difficult. So these are going to be slightly more difficult because of the same reasons that we talked about for uh, pyridine and pyrimidine. Both of these are going to undergo electrophilic aromatic substitution, and usually these undergo a number of different reactions, so we get different products here. So if we have something like this, which is going to be quinoline, we can brominate this in a product solvent, and we will get a mixture of 2 products because electrophilic aromatic substitution is not necessarily easy for these compounds. All right, so we can have both of these rings. If we then change this to an isoquinoline, which is just moving the nitrogen 1 position over on the ring, and we do the same reaction conditions, we can then get a more favorable mixture of substitution on the carbon atoms that are farther away from the electron withdrawing nitrogen. So this is about a 50-50 ratio, and then this is going to be about a 90 to 10% ratio. And then if we were to replace the nitrogen 6-member ring with pyro-like nitrogen ring, then this will undergo electrophilic aromatic substitution a little bit more easier. The same reason that pyrrole undergoes electrophilic aromatic substitution easier as well. And so this has, if we take a look at this structure, we can make something that looks like this. So we have the aromatic contribution of the lone pair electrons from the nitrogen, and this is not going to be acidic or not basic amine because protonation destroys aromaticity. So we're not going to have protonation of this amine here, so it's more easily undergoes aromatic substitution. So we can do this at lower temperatures and dioxane and brominate this, and we will actually get substitution on the ring where the nitrogen is located. And so that'll be where we end. We're looking at the heterocycles. So we looked over polycyclic heterocycles, their difficulty in undergoing electrophilic aromatic substitution, and also their relevance in terms of biomolecules. They show up in nature a lot. Then we looked at the low reactivity of pyrimidine and pyridine towards electrophilic aromatic substitution because of the dipole that's created there, and also the fact that this amine is going to be more basic than it is for pyrrole. And so and that has to do with the fact that the lone pair electrons are going to be in the unhybridized p orbital, so they're not available to form acid-base complexes, and also because of the dipole moment there. And then we also looked at pyrrole and imidazole, and these are the easiest to undergo electrophilic substitutions and why they go in the C2 position over the C3 position because of the extra resonance stabilization they have. So we'll end there for our heterocycles, and then next time we're going to talk about the spectroscopy of amines.